quantum mechanics. I'm Emmanuel. You are Maxim. And you are? David. And you are?
No.
Okay, we're gonna have to spell it.
K-E-H-A-O. Yeah, that's my first name.
So, Kaho?
Yeah.
Kind of, okay. I'm probably not saying it correct, but close
No,
enough.
no.
You know who I mean. This semester is a weird semester. Not only that it started late, it's going to be 10 weeks, it's going to be hybrid, it's going to be also on Zoom. What does it mean for you? Not much. From your perspective, it's a pretty usual semester, meaning there's going to be homework, there's going to be an exam at the end. The homework are going to be 30% homework. The grade is going to be the grade is going to be 30% homework and 70% exam. I'm in charge of the homework. Professor Richard Berkovich is in charge of the exam. You already had a lecture with him?
Yeah.
Okay, how was?
Long.
Long, yeah, I'm sure it was. The only difference between this semester and usual ones as far as you're concerned, are the fact that it's only 10 weeks, therefore we cut some of the material. Meaning what we're instructed, and it makes sense in my eyes, is that we're not supposed to make 14 weeks fit somehow magically, miraculously to 10 by putting loads of work on you. On the other hand, what we are instructed to do is just to take off material. So in this course, it's pretty natural to just cut off the last end. That's going to be pretty usual. One last thing, anyone who is in the Miluim, serving in reserve units, or their families, or any other things that have to do with the war, please let me know. It might affect my willingness to let you submit homework late. In general, one of the things we're instructed to is to try not let you submit homework late because we don't want you to create gaps. Any questions, or I should start? Okay. So, my speaking English is pretty good, I think. My spoken English is okay. My written one is not amazing. So I'm going to do typos. I'm going to do spelling mistakes. You'll be fine with it. Good luck. Mathematical. This is for you. Introduction. Okay, we'll do mathematical introduction for things that, assumingly, you're gonna know you know already, and no one knows how to write Fourier, right? At least I don't. F-U-R-I-E-E-R. So whoever was a very, very strong student last year does not need this class. Oh, wait a second. Did you do? Yeah, some of you do, because you didn't all do Mathematica 3. So you do need this class, and it's good that I'm aware of it. So we're going to start with Fourier series that you're supposed to be familiar with from last year. Tour Fourier. Sometimes I will translate myself to Hebrew just for like one word, but I will not add any information in Hebrew that I did not say in English. Then we'll do Fourier transform, which is something that you will see this semester in the course Math 3. It is something that's very, very basic in this course. Then we'll talk about the delta function. And depending on time, we'll also talk about matrix, linear algebra, matrix stuff.
All of this today.
Yes. It's gonna be fun. Okay, let's start with Fourier series. What is Fourier series? You're all. How aware are you? Are you of Fourier series? How well do you remember it?
Sum of sinus and sinus cosine.
Yes, sum, sine, cosine. So we have a certain function. This function is a periodical, meaning, for example, I can talk about y of x is equal to absolute value of x, where x is between minus L and L, or minus L over 2 and L over 2. What does it look like? It looks like this, right? What do you want to talk about it? Yes. Let's do it, for example, from minus 1 to 1. Okay? So what does it mean? It means that the real function is, Yair is here. Hi Yair. It means that the function that we're actually describing is periodic. So it goes like this. This is the function. It goes from minus infinity to infinity. And how do I describe this function? Like this. I just described it. Y is equal to absolute value of x. X is between minus 1 and 1. Okay. This function is fully described. I know how to plot it. I know what is y of x is equal to 34. It's somewhere between 0 and 1. I don't know what it is. But I can keep on going until I get there and know what it is. Now, there is an important way of describing this function through a sum of sines and cosines. What is the okay, this would be highly unprofessional. Yes. Did I? No, I did not. Sorry. Forgot. F of x is a0 over 2 plus sum of an, you see all the way to the end, yes, cosine of n pi x over L. Do you see all the way to the end? I think we can do it. Plus sum of bn sine of the same argument, n pi x over L.
Fully.
Yeah. I won't write here in the future. And it goes from 1 to infinity. Where a0 is the integral of f of x from minus L to L dx. I wanted to do a 1 over L here. Yes, 1 over L. An is 1 over L, integral from minus L to L. Cosine of n pi x over L, f of x dx. And bn's are the same, just with the sinus. Okay. So these are this is the algorithm, if you wish. So now if I want to describe this function using sine and cosines, I can do that. It's going to be through a sum of infinite components. How do I calculate them? I start by calculating this. So in this case, a0 is going to be 1 times the integral from minus 1 to 1 over the absolute value of x dx. This is an even function. So I can say that it's 2 times the integral from 0 to 1 of x dx, which is 2 times x squared over 2 from 0 to 1, and I get 1. Okay, this wasn't too hard. Is this too easy? Is this too boring? Well, maybe it is. I don't know. Okay, an is going to be 1 over L times the integral of x times cosine. Now, I'm just going to take the right-hand side because it's an even function again. I'm going to write a 2 here and do the integral from 0 to 1 of x cosine n pi x over L dx. How do I solve this thing? Do you agree this is the term this is what I want to solve now? I multiplied it by 2 because I took only the... Okay, let's recap. Cosine is an even function. f of x in our specific case is absolute value of x. Absolute value of x is also an even function. Multiplying two even functions by each other gives me an even function. When I have an integral over an even function, I can just take half of it and multiply by 2. Okay, so that's what I did. I multiply by 2, 2 over L. The integral goes now not from -1 to 1, but from 0 to 1. You're sitting in a very bad place. Like you chose the worst seat in the class. You had 1, 2, 3, 1, 2, 3, 4, 5, 6. You had 18 chairs. Oh, good. Sorry. But did you sit always on the front row right hand side? It's a thing. Okay. I have this. The way to solve this is by parts. Hi, you are?
Joseph.
Joseph. Hello, Joseph.
Hi.
Are you Joseph? Or
Yes.
Joseph?
Whatever you
לא
like.
ישראל.
What?
לא ישראל.
Oh.
No, usually.
Oh, yeah, that.
הקוונטים?
Yes. Shalom.
שלום.
How are you? What's your name?
אורי.
Ori. Okay. So what we started with a quick revisor of what is a Fourier series. From this, we're going to jump to the Fourier transform, delta function, and matrix stuff. Basically, this class today is mathematical introduction. Okay. The way to solve it is by parts. So I define f as x. F prime is going to be 1. G prime is going to be cosine of n pi x over L. And G is going to be, what's the integral of cosine? Yay, it's a sine. Sine of n pi x over L. I need to divide it by the inner, whatever, inner derivative.
Yes.
So divided by n pi over L. Therefore, this integral gives me f times g. So I have x times sine n pi x over L over n pi over L. What is my L here?
1.
Yay, L is 1. So I can just ignore this. Okay, also the L here becomes a 1. And also the L here. I should have done it a while ago. From 0 to 1 minus the integral of this times this. So 1 over n pi, the integral of sine n pi x dx from 0 to 1. This is equal to, well here when I put the lower limit at 0, I have here sine n pi over n pi. What is sine n pi?
0.
Yay, all this dies. Okay, what I have here is the integral over sine. The integral over sine is a cosine.
Right.
And I'm, oh. I have the minus, so let's do 1 over n pi. I have also the I have the minus here, another minus because the integral is minus cosine. So I have cosine of n pi x between 0 and 1. What?
It's in square and 1 divided by n pi in square.
Yes, it is squared. Thank you. Okay. Maybe I should start looking at my notes at some point. I will at some point when I'll lose my last bit of confidence I have. You're doing a good job at it, by the way. When I put the lower limit, it gives me minus 1. When I
עמנואל, אני חושב שחסר לך מינוס ב...
No, it's הנגזרת הפנימית.
and the integral of sine is
לא.
minus cosine and I have this mine.
באיפה שסימנת. G-tag. ואז שאם נגיד אתה גוזר...
If I do an integral over cosine, I get a sine.
אינטגרציה.
אוקיי.
כן, הנגזרת עשינו זה קוסינוס.
He's right?
מינוס קוסינוס.
פונקציה קדומה, לא נגזרת.
אם אתה עושה נגזרת ל-G...
Oh yeah. I'm missing a minus here.
בסדר?
Okay, this changes everything. our lines are separated too. So this is still 0, thankfully. You're saying here it should be a plus.
Yeah.
Therefore here it should be a minus. And I should look at my notes.
And now it's plus because the first term is negative and the second also is negative with the
Yeah,
minus.
so now if let's do a plus here and change the limits.
Right.
Okay, if I put in now the lower side, the 0, so I have, well, n pi squared. If I put now the lower one, I have minus 1 minus minus 1 to the power of n. What?
You write in
מינוס
the
קוסינוס.
no, if you develop the
Derivative of sinus is cosine.
cosine.
Yeah, but here I take this is the derivative, so this is the integral. Here, from here to here, I integrate over g. Okay, so this depends. If n is even, so I get a 0. If n is odd, so I get a 2 over n pi squared. That's what I'm supposed to get. Where is this? Here it is. No, I'm wrong. I forgot the 2. I had a 2 here. Ah, I did it on purpose. I wanted you to catch me. So I have the 2 here, the 2 here, and the 4 here, and the 2 here, which makes it 4. Would make this to be a 4. And it says here it's supposed to be a minus. Well, now I'm debating which one is
The
wrong.
derivative of sine is cosine, so the integral for cosine is meant to be a sine.
You're saying this is what? No, this I
You
want
do
to
an
find.
integral of cosinus, you get a sine, not a minus.
Yeah, it was right the first time.
It was right the first time.
Yes.
I should not believe you, at all, ever. An integral cosinus is sinus. Yes. Ay, ay, ay. Okay. And so I calculated this. This one is going to be the easiest because I did the integral of x minus 1 to 1 of x sine n pi x. And this is an even function. This is an odd function. Odd function multiplying an even function and an odd function gives me an odd function. Integral and symmetric limits on an odd function gives me a 0. Therefore, I can conclude that the function f of x, which is x between minus 1 and 1, is the a0 was 1. I'm supposed to put here a half plus the sum of this summation gives me 0 because the b ends are 0. What I have here is the a ends, which is minus 4 over. How do I talk only about odd numbers? I do 2m minus 1 pi squared. M goes from 1 to infinity. Cosine of 2m minus 1 pi x. Yay, we got to the Fourier series. This is a Fourier series. So what am I doing here? I'm taking here an infinite number of cosines, summing them, each one with its weight. This thing here is the weight. So the first cosine has one weight, the second one has another, etc., etc. Summing over there gives me another function. Okay, this is no surprise. Now, how do I get to these equations? Do any of you remember?
By the inner product. Okay, so you have a basis of functions, and you're taking the inner product,
The orthogonality.
like here the integral.
The orthogonality.
Those what?
The orthogonality of the sets.
Orthogonality. Yes, exactly. So you both said the right answer. The way to get that is through using the fact that sines and cosines are orthogonal. So this is something we'll talk about maybe now.
Right.
What?
Oh, it's kind of the same.
Hey, you meant the same thing, yeah. You both put the right answer, yes.
Yeah.
Except in different words then.
Yes.
Both words. Where are you from?
Mexico. Mexico.
Mexico. Is it Mexico or Mexico? Is that
Mexico.
is it Mexico?
Yes.
And why do other people say Mexico? Because of the X?
And it's in English or in Spanish.
So let's talk about orthogonality. It has to do with these three series. So first, I'll soon show you how. Orthogonality. So, what is orthogonality? What does it mean? So you all know that if I have the vectors 1 and 0 and 1, if you wish I can. If I have vectors A times vector B is equal to 0, these two are orthogonal. This is the definition of something orthogonal. What does it mean? How do I show it? Usually the way to show it is by multiplying A1, A2, A3, not usually. This is the definition. What? Is equal to 0, right? So not exactly. Something else is part of the definition that sometimes you forget is that these ones, we take the complex conjugate. This is a definition of orthogonality. When these two are equal to 0, it is orthogonal. Okay, for example, I don't know, 1, 0 times 0, 1 is orthogonal. Another way of saying the exact same thing is to say that A, B are orthogonal. Okay, this is the notation you never saw in your life, right? Have you seen it? Joseph has seen it. And so have you. I forgot your name. It starts with a K and it has an O at the end.
Yeah.
Kaha.
Yeah.
Okay. Slowly. I'm going to ask things a few times. Okay. Yes, okay. Usually I'm weaker. So this thing is called bra. And this thing here is called kit. What does it make together?
Bracket.
Bracket. It's cool because it's a bracket. Good. Okay, so this thing here means a row vector, but taking the complex conjugate of it. This thing here means a column vector without taking the complex conjugate. Okay, so if I tell you that my elements are 1 plus I, if A is equal 1 plus I, 2, and I, so the vector A would be 1 minus I, 2, and minus I. Okay, this is just a notation. Okay, what happens when we first met the word orthogonal? We confused it with another word called perpendicular. Right? We said, okay, it basically means 90 degrees. Sorry, not 90 degrees. I meant pi over 2. Right? And then later we understood that we can talk about more dimensions than 3. For example, 4 or 5 or infinity. Now, what happens when you talk about a vector of length infinity? So it's way more friendly to talk about it as a function. Okay, think about it this way. So we have here a vector of dimension 3, so I can talk about, let's use the letter J. J is equal to 1, J is equal to 3, so I can have here AJ, A1 is here, A2 is here, and A3 is here. But if I have an infinite number of numbers, so I can just put a line through them and get a function. So a funny way of defining a function would be a vector with an infinite amount of elements. How do you define orthogonality there? Yes.
That's a Fourier series, right?
Before,
You're
yes.
making-
What?
You have an infinite number of bases, and that's what you're calling them.
Yes, that's the connection. Exactly. So we'll talk about it very soon. Now, also when I talk about function, I can talk about orthogonality. Okay, just like here, I can say that these two are orthogonal. I can also define orthogonality when I talk about functions. How is it defined? It is defined for some reason through an integral. So I'm going to erase everything. Is that okay? Wait once. No, you're still copying.
Because it's a projection, right? And the integral is the area under the curve, so it's kind of the same concept, but applied in different.
Exactly. It is confusing at first.
Yes.
We good? How old is this room? I've never been here. Was it like this also before the war?
The newest one. The newest one in the building.
Oh wow. In order to say such a statement, you need to know all the rooms in the building.
This room is new. מרחב למידה.
So, the definition of orthogonality is, as I said, defined through an integral. So, for example, I can show it about the sines and the cosines before. So, if I want to show sine and cosine of the truth, I would need to show different things. Let's just show it about e to the ix. E to the I n pi x over L and the plus minus, okay? E to the plus one, okay? E to the I n pi x over L. You know that if I take positive and negative exponents, we can get the sine and cosine through Euler or whatever. I want to show that these two are orthogonal. Well, I mean these two. If I take e to the I n pi x over L, and instead of n I take an m, a different letter, so they're orthogonal. What would it mean if my phi n, let's say phi n of x, is this? So I want to show that phi n, phi m are orthogonal. I just add something. Is this orthogonal? No, wait a second. Delta n means that
0 if n and n is 1.
I added here something else, not just orthogonal, also orthonormal. Aha! So in order to do this, I need to add here 1 over square root of L, I think? Yes, 1 over square root of L. Now it is weighted, and now we'll see that this is true. If I show this is true, then I show that these functions are orthogonal, or orthonormal, and they span in bases. The poris merchal. Okay, how do I show this? I need to take the integral from. I'm talking about these functions defined between minus L and L, which is exactly what we spoke about before during the Fourier series. If I take from minus L to L, 1 over square root of L e to the minus I n pi x over L times 1 over square root of L e to the plus I m pi x over L dx. So this is phi n, but I took the complex conjugate because it's in the bra. This is the ket, so I did not take the complex conjugate. Here there's an m, here there's an m. This is 1 over L. I think I want to have like 5 erasers in like different places. On the other hand, this one is a horrible one. But I get 1 over L, the integral of e to the I m minus n pi x over L dx. There's different ways of solving it. The easiest one is to use now Euler, 1 over L times integral from minus L to L of cosine of this discussingness m minus n pi x over L plus I sine of the same thing. This is if n is different than m, so it gives me a 0. How do I see this? It's a sinus over a full cycle, or a cosine over a full cycle, and gives me a 0. What happens when n is equal to m? Ooh, let's see. So here I have sine of 0. Sine of 0 is 0. Okay, and here I have cosine of 0. Cosine of 0 is 1. So I have, I made a mistake.
It should be
It's
divided
supposed to
by
be L over 2. Sorry about that. And then I get a 1. So these functions define between minus L over 2 to L over 2 are orthogonal. It works on the same.
Manuel,
Yes.
aren't you missing a factor of pi somewhere?
Of what?
A factor of pi somewhere.
Yes, I am. I must be missing because wait a second. Why am I missing an L, a pi?
I'm just looking at the integral and I'm trying to figure out if you're gonna get. Oh, because
I integrate over 0. Like this thing here. If you're talking about the case that m is equal to n, right?
right.
If m is equal to n, so this here is a 1.
0. It is a 1.
Cosine of 0, which is
Right.
1.
Yeah.
Independent of pi. I do need pi for it to be defined as a full cycle here.
Okay.
So now I'm debating whether to show you how from this I get to that. Is there any point in showing it? Oh, okay. If you would have said yes, I would have done it. But silence means no. Okay. I'm going to erase everything. So, foreign students. When did you come to Israel?
3 weeks ago.
10 days ago.
Were you debating whether to come here because of the war?
No.
That is okay.
3 weeks and 10 days. 10 days, you're still jet lagged.
I came here December 15th. More than 10 days.
So, and okay. So now let's talk about Fourier transform. Should I show you how we get to this? No. Okay. Basically, what?
You have to multiply by both sides and integrate.
Yeah. You start with this. Basically, all sines and cosines are orthogonal to each other. I multiply both sides here by cosine m pi x over L, for example. Let's see. Cosine of m pi x over L. I multiply this by cosine of n pi x over L, and I multiply this by the same and this by the same, and I integrate from minus L to L, and from minus L over 2 to L over 2.
I think over 2, right?
You think by 2? Whatever. Okay. Oh, and I also... Okay. So, once I do this, so here I get an integral of cosine over full cycle. It's going to give me a 0. Here I get, again, sine and cosine multiplied by each other is odd. When I integrate over a full cycle, it gives me a 0. I'm only left with this. What am I left with? Integral of f of x cosine of m pi x over L dx is equal to the summation of an cos m pi x over L cos m pi x over L integral dx. And then because I'm a physicist and not a mathematician, then I can change the order of the summation and the integration.
Right.
When I change the order, so, well, even if I don't change the order, I can see that this fishes out the n equals m component, otherwise I get a 0. All others cancel each other out. So I'm left here with am cos m pi x over L dx. I integrate, I get the m pi over L out, etc. And I get that. Okay, what happens? Okay, which of you here has learned about the Fourier transform?
in the wave.
Oh, wave is in first year? Are you second year or first year?
Second year.
You're second year, so when did you learn waves?
In the summer.
Was it mandatory to do waves before this course?
Yeah.
Okay, so I can assume that you know Fourier series. That's a good thing. Fourier transform.
We're serious, we learn in Memphis too.
Yes, with me.
Yeah.
Good times, good times.
You said last year that you're going to leave the university. But you are staying.
That's why you say it, and then you see that I'm still here.
Yeah.
I was being also very dramatic about it. I was being very dramatic about it. Yeah.
You was excited.
What?
You was excited to leave.
I was excited to leave? No, I wasn't. I love it here. I wish I could stay here forever. So, if I take the limits from minus L to L and minus L over 2 to L over 2 to infinity, what I get is a Fourier transform. I will not prove it or show why it's true. I'm just going to write it. It's going to be very, very needed over this course. So you do need a refresher is always good. Fourier. That's how we write it. Yes? Yes. No, I got it.
With an O.
Always forget how to write it. These French people. Do you remember what I said about Fourier?
Sadly no.
What?
Sadly no.
What?
Sadly no. I don't remember.
Do you remember how he died? Come on, I told you at least twice last year.
I was saying the other book with Jonathan.
Okay, Fourier was French with Napoleon. He ruled over some part of Egypt. He believed what? No, he believed the earth is too cold. So he rocked around with the blanket around himself. Once he stepped over the blanket, tripped and died. So, Fourier transform. F of x is equal to integral minus infinity to infinity dk over 2 pi, square root of 2 pi, e to the ikx f tilde of x, of k, sorry. It's the whole point, Emmanuel. While f of k is equal to the integral from minus infinity to infinity dx over square root of 2 pi e to the minus ikx f of x. Okay, so I could talk about the most frequent example is time and frequency. I can talk about everything in the world in terms of time, or everything in terms of frequency, and it is both options are completely kosher. Why is that? Because it's fully described. I can, if I tell you something in the language of time, and I'm asking you to translate it, and you know exactly how to translate it to frequency and back to time and get the exact same result, so it is fully defined. In different courses, sometimes we just divide by 2 pi here and not here, right? Did you see these things?
Yeah.
So that's very, very annoying. This is what I'm going to be doing in this semester. I think it's way easier. You just have to divide by 2 pi going both ways. And here there's a plus, here there's a minus, and okay, that's it.
The tilde in the FK, the F.
Yes, what about it? Okay. What are properties? Some properties, I think some of them you might have to use in the homework that I did not upload yet, but I will upload later today, are linearity, where f, and then some dramatic f like that, of a f of x plus b g of x. If I do a transformation of f and g, but I add them together and multiply them by constants a and b, are just like a doing the Fourier transform. I don't know how to write these nice f's, right? There's like some fancy f that you write. I don't know. F of x plus b f of g of x, which is a f tilde of k plus b g tilde of k. Okay. The next one is about a shift, where if you do the transformation of f of x plus x naught, meaning I move the function in x, how does it affect the function in k? It will be f tilde of k times e to the I k x naught. Multiplying, shifting here is multiplying by this exponent there. Derivative. Well, if I do the Fourier transform of f prime of x, it will be like multiplying here by ik. It's going to be ik f tilde of k, and scaling if I multiply x by a certain constant a, it is 1 over a f tilde of k over a. Okay, so if I multiply it here, I make it, if I make something bigger here, I make it smaller here, something like that, right? This is going to be something generic in this course. We'll talk about it again and explain myself more in a few minutes. Okay, these are 4 properties of Fourier transformation. And now I will want to do the transformation of a Gaussian. It's an example that if you learned Fourier transform, you probably see it's a very classical one. What happens if I do the Fourier transform of a very narrow Gaussian?
You get a Gaussian.
Yep. Joseph?
You get a Gaussian.
I get a Gaussian.
It's Gaussian and it will be more
It will be wider.
wider.
If I do the transformation of a wide Gaussian, it's going to be a narrow one. So, okay, if f of x is equal to e to the minus alpha x squared, and the integral over from minus infinity to infinity over e to the minus a y squared dy is equal to square root of pi over a, what would be the transformation of this? Do you remember how to show this?
Yes.
There's a few ways of doing it. It has nothing to do with our course. Yes, how do you show this?
You can go by complex variable or to polar coordinates.
Very good. There's more ways, but this is it's a fun riddle, I think. You remember that?
Yeah,
Yeah.
the polarization.
Yeah. If you move it to polar coordinates, so you can get y squared, and you do also x squared, y squared plus x squared is r squared, but then you get a Jacobian, and the Jacobian saves you. It's fun stuff. Do you remember? Okay, whatever. The Jacobian is called after, what was his name? Carl Gustav Jacob Jacobi. He was very Jewish, and his parents had really Jewish names, biblical names. Shimon and Rachel. Simeon and Rachel, I guess. I find it like a funny trivia knowledge. So f tilde of k would be 1 over square root of 2 pi, integral from minus infinity to infinity, e to the do you take the plus or the minus here? I don't remember. F tilde of k is going to be with a minus. Minus I kx, and now I need to write the actual function, minus alpha x squared dx. This is the integral I need to solve now. How do I solve this?
By completing the square.
I want to put what?
By
Combining the two exponents. Okay? And I'm going to start copying from my... I hate this part. Meaning I love it. It's a fun challenge not to miss any minus, but it would be very, very shameful to do it in front of you. I'm just going to copy from here. It is 1 over square root of 2 pi, integral dx. By the way to remember, of course, if I want to get a function of a k, I need to get rid of the x. The way to get rid of the x is integrating dx. Now I have here exponent of minus alpha times x plus ik over 2 alpha squared minus k squared over 4 alpha. Okay, let's just see that it makes sense. If I look at the x squared component, I get e to the minus alpha x squared. E to the minus alpha x squared. That's good. If I look at what everything has to do with k squared, I want it to be 0 because here I don't have any k squared. Here I have minus k squared over 4 alpha. Here I would have minus alpha times ik over 2 alpha squared. What is this? This is this times this squared. It is plus alpha k squared over 4, right? You see this? I'm talking about, okay, my whiteboard is getting messy and not white. I'm talking now about this component. This is the b squared. It is multiplied by minus alpha from outside. I get to this, which cancel each other out with this. And finally, if I look at the 2ab component, I get minus alpha x I k divided by alpha, which is minus I kx, which is this. So getting there would take me 3 lines. Showing that it's right takes me 2.5. Okay, what is the integral of this? Here I have an exponent of, well, we know that e to the a plus b is e to the a times e to the b, but here my b is a constant. Is it a constant? It's a function of k.
But you can put it
But I'm
over
integraling
into,
dx, so it is a constant. So I get here e to the minus k squared over 4 alpha, which is a Gaussian. Okay. Time the integral over this.
and divided by the square of 2 pi, right?
Yeah. Divided by the square root of 2 pi times the integral from minus infinity to infinity over e to the minus alpha x plus I squared over 2 alpha squared. Now, I could define, do I have a y here? Yeah, let's define y. Y will be x plus ik over 2 alpha. dy is dx when x goes from minus infinity to infinity, so y also goes from minus infinity to infinity. Therefore, I get e to the minus k squared over 4 alpha over square root of 2 pi times this integral, which is simply, it's this, right? Where this is my alpha. Was it alpha or a? I think it started off with an a. No, it was an alpha all along. So I have here the square root of pi over a, square root of pi cancel each other out. I get e to the minus minus k over 4 alpha divided by 2 alpha. Yes? Okay. What did I learn here? Why did I do this? Well, when we spoke about waves, we spoke a lot about time as opposed to frequency. Here we're going to talk about something else. We're going to talk about location and momentum. Location is going to be x, and momentum is going to be with the letter k, just like before you had time and frequency. Okay, so we're not going to talk about the time. The time. Mimad zman dimension.
Yes,
The time dimension and the frequency dimension. We are going to talk instead about location dimension and the momentum dimension. And something that you know that you might have heard from popular science. When you know a particle's location, when you have full knowledge about the location, you have zero knowledge about the momentum, and vice versa. For example, if I know the momentum, if I know with very good accuracy the location, so my A is very, very big. Should be carries very strongly. I know I'm exactly at the origin. So my knowledge about the momentum is very, very wide, spreads, and vice versa. When alpha is very, very small, so my knowledge about the momentum is very, very specific. I know exactly my velocity. I have zero knowledge about my location. Okay, this is called uncertainty principle. Yay! So at the end, we are talking about quantum mechanics. Not really. This is just a mathematical introduction, but this is a very, very basic concept. It's also a way to see that you make sense. That you're not completely off. If I ask you something about the location, about the momentum, and you got two very specific answers, you're probably wrong. Okay. I think in the homework I'm going to ask you some Fourier transform. Please transform. Show me what are the Fourier transform of this, and that. This should be fine with you. Any questions about this? Okay. Oh, yeah, nice. תעשה לי בינתיים דסמוס עם גאוסיאן שנראה כמה זה יפה. עם מה לך, כן?
השאלה בעצם תשאל מה... Fourier transform של מה?
I'm going to give you a function. I'm going to ask you to do the Fourier transform. Meanwhile, while I'm erasing the whiteboard, Maxime is going to show us.
The last line. The k is supposed to be in the...
Square, yes. Square square. Maybe it was before and then you erased it. Maybe not. Like this? It is, also here it was. No, just write A. No, write A. Add slider A. Yeah, now play around with it. It's gonna be fun.
תעשה פליי.
Wow. Isn't it fun?
תעשה לו גבול שזה...
Yeah, I guess it needs to be positive.
Yes, it can go on the positive.
Have you ever used this? Desmos? Right, it's fun. Yeah, you see how now it's narrow, and the other one is going to be wide, and we're going to have lots of fun.
Delta, right?
What?
When you make it infinitely big,
We're making it very, very narrow.
yes.
So?
You get a delta function, right?
Yes. So we're going to talk, and by this, Joseph is leading us to the next part of our lesson. We're going to talk about the delta function. So, the delta function we spoke about before was delta of Kronekel's delta. Yes, yeah, you can leave it. I just thought it's fun while I'm erasing the whiteboard. We all have fun, right? The thing that causes pleasure as physicists. When I spoke before about Tifter has left our meeting. I guess I disappointed him. Okay, I showed you before that cosine of something times sine of something was delta of n comma n. This is delta of Kronekel showing it is
Discrete. Discrete?
Discrete. Oh yeah, you said it. Yes, discrete. It was a discrete variable. Now I'm going to talk about the representation where it is continuous, and it is delta of x minus x naught, for example. This is delta of Dirac. Who here is delta of Dirac? Okay. So,
We saw that in the Memphis tree. But
oh, so you did see it. Good.
Oh, so wait.
Jonathan did not explain this.
This?
Yeah.
You mean how they're connected to each other?
Yeah.
Okay, so I probably won't highlight more than he did because this is one of the jobs of his course. We're just going to use it over this course, so it's a good time to mention it and to quickly revise it. Also, this is going to be in the homework, I think. Some maybe proving some of the identities of the delta function. You know before that if I have here an times delta nm, n goes from A to B, and m is between A and B. What happens here? Average random summation over A ends. The ends start at A and end at B. Now suddenly I multiply by a delta. The delta is fishing. That's how, in Hebrew it's completely legitimate to use the word fishing in such a context. I have no idea if it works in English. But it's fishing out the one element I do need. That's what we did before, getting to the function of the Fourier series. So when I do it here, it takes out, it pulls out the one component that is relevant, which is going to be an. I get only one element out of all of them. This is where, with discrete variables, what happens with continuous variables. We're going to do here an integral from A to B. Integral dx. A certain function of x times delta of x minus x naught. This delta is going to make sure if x naught is within A and B, it's going to pull out, it's going to make sure to take out exactly f of x naught. So this is how these two functions are similar. Delta here is for discrete, delta here is for continuous. Okay, now there's a question of, well, there's a, here if I take the sum of delta n m, let's do it this way, delta n m, when n goes from A to B, so just count the delta itself. Delta itself is either 0 or 1, right? What do I get?
1.
1, because 1, specifically for n equals m, I get 1, and all the others are 0. Which is what physicists think. I think it was funny. No? Whatever. I have a very silly sense of humor. The parallel to that is the integral from a to b, or usually we take it from minus infinity to infinity. Dx times delta of x minus x naught is going to be 1. So these two things are just comparing the two deltas, generalizing the discrete one to a continuous one, showing you here two properties. If I integrate it from minus infinity to infinity, I must get a 1. And if I integrate it times the function, I'm supposed to get the function at x naught. How do I get to this function? What is this function? So this function is not a real function, meaning it's a weird one. It's at the origin it explodes. What do I know about it? Well, let's show you some of the representation. If you go to Wikipedia, you can probably see more. Some of the representations of delta function, one of them is, for example, a very, very narrow Gaussian. Well, one way of showing it is like this. Delta of x can be the limit of epsilon goes to 0 plus 1 over pi epsilon divided by x squared plus epsilon squared. Another would be delta of x is equal to limit of epsilon goes to 0 plus 1 over square root of pi epsilon e to the minus x over epsilon squared. The last one, which is equal to limit of epsilon goes again to 0 plus 1 over pi sine of x over epsilon divided by x. Once I had a question in my research. My advisor told me to go to another professor here, and he helped me out. We sat together for like an hour. He explained to me something, and then at some point we got to this. He said, "This, of course, is a delta function." And I was like, "Wait a second, what is this thing?" It's a sinc. It's a sinc function. Like, I didn't immediately see that it's a delta function. To which he told me, "Emmanuel, if the KGB wake up a physicist in the middle of the night and ask them what this is, you must tell them it's a delta function." So each one with his.
It's like the function that it's very important in optics, right? That it's.
Yeah, in optics we use it all the time. Yes. So these three things are representations of the delta function. How can I show it? Well, I can integrate it from minus infinity to infinity and get a 1. I can integrate it times a certain function and I can get a certain function at x naught, or at the origin. Of course, if I take instead of x, I do x minus x naught, I'm going to get delta of x minus x naught, yes? So just moving it to the side. Now, two more things that are true about all these delta functions is the delta limit. Should I show it this way? Yeah. I'm going to show it in a more practical way. Delta of x goes x is equal to 0 goes to infinity, and delta of x goes to
No, not 0.
x should be 0. Right? The simplest way to imagine a function, as since you're all nodding intensely, I don't feel like I need to talk about it too much, but when they started teaching us about the delta function, what they told us at the beginning, which is the easiest way to imagine it, is a very tall rectangle, right? It is h, its height is h, and its width is 1 over h, and I can very easily see that its surface is 1, and I can see that at x naught, h of course goes to infinity. I can see here, the delta is 0, and here delta is infinity. Now let's show that these properties, 1, 2, and 3, are true about which representation? About the Gaussian representation. I'm going to erase everything. Going once, going twice. Who is at home? Sean and Tifto. I'm not really talking to you guys. I'm not even looking at the camera in the back of the room. If you have any questions, please feel free to ask. I want to show that these three properties are true to this representation of delta. So, let's start with the first one. When x is 0, if x here is 0, so I get here 1 limit of epsilon goes to 0 plus 1 over square root of pi times epsilon times e, this is not epsilon times e to the power of 0. What is this?
1.
What? No, e to the 0 is 1. What is this whole thing? Infinity. Okay, what happens when x is not 0? So here I have again limit of epsilon goes to 0 plus. I get here 1 over square root of pi, and we lost John. And I have here e to the minus x over epsilon squared. Well, you know that a Gaussian, and I have here an epsilon, of course. So on the one hand, I have a Gaussian taking me to 0. On the other hand, I have an epsilon in the denominator making me explode. Who's going to win? How do we do this? You can do L'Hopital or whatever you want, but of course, e to the an exponent is very strong. An exponent to the x squared is even stronger. Of course, the exponent is going to beat this, and then it goes to 0. I can show you doing L'Hopital, but you know how to do that. At last, let's integrate it. This is going to be fun. Do you know what's the integral of a Gaussian? Did we do something like that before? Oh, let's use it. It might be efficient here. Okay, it might help us out. So, what I have here is limit of 1 over square root of pi epsilon, pi times epsilon. And now I want to integrate from minus infinity to infinity, e to the minus x over epsilon squared dx. Okay, this is just like having the a here as 1 over epsilon squared. Therefore, it gives me limit of epsilon goes to 0 plus. I have here 1 over square root of pi times epsilon times square root of pi epsilon squared. This is equal to 1, and it makes us all super duper happy. Okay, let's do some properties of delta function. Delta function with whatever representation has the following properties. This marker is getting even more tired than you. Next time I'm going to bring more markers and the class is going to be super colorful. Well, it is symmetric, which means delta of x is equal to delta of minus x. There's scaling. Delta of ax is delta of x divided by the absolute value of a. And oh, there's another one. I don't know why it's here. It's confusing. Maybe I shouldn't write it. No. Okay. Okay. And there's another example here, which is Fourier transform over delta function. Should I do it?
It's a sign, right?
Just a second. Depends which representation you take. Whatever. This is not important. Last thing I want to do is remind you how to diagonalize a matrix. Why? Because it's going to be useful in the semester. And let's see it now when our minds are so fresh. When I say diagonalize, what I mean is to find the eigenvectors and the eigenvalues. Oh, this one I wanted. So let's say that I have a matrix M, which is 0, delta, delta, 0, 0, 0, 0, 0, epsilon. Let's make it not too hard on us, okay? Why am I doing this? Because this, if we'll get to have a matrix on our final exam or in our homework, this is going to be the kind of matrix we have. What this here represents, for example, is a molecule consisting of 3 atoms. This is usually what I teach in week 11th of a regular semester. See here, there's an 11. But this semester we're not going to have an 11th course. An 11th week, so I have no idea what we'll get. I do want to tell you what the concept is. The one is the context in which this is related to quantum mechanics. I have an electron. The electron can be here, or here, or here. There's only one electron. I don't know where it is. Where is it? Is it in a stupid position of all three sets? And when something else I wanted to do is talk a little bit about the statistical nature of quantum mechanics. It is confusing. When I say statistical, like when I say the electron can be in a few places at the same time, what does it mean? Can it actually be in a few places at the same time, or is it just a statistical property? What kind of statistical property is it? When I see the mean location of the electron is here, what does it mean? What does it mean? What we're talking about is, did you see the video of Rachel's video with 2 slits?
Yes.
Good. So I have 2 slits. I want to do something that I just find it important at some point to mention it. If I have 2 slits, I have here. How do you say tabkhut? How do you call this pattern? Tabkhut.
Interference.
Yeah, it's interference. Right? That's what you call it. Okay, so you have your. I think it's interference. Interference alpha.
גם וגם.
התאבכות. התאבכות בונה, התאבכות הורסת. You have two waves that are exactly the same, so they build each other, they help each other out, right? Is interference?
Yes.
Okay, interference, good. So, what does this pattern mean? What this thing means is not that the electron is going to be also, most of it is going to be here and most of it is going to be here. No. If you have one electron, so we have only one electron. There's a very high chance of finding it here, a low chance of finding it here, and zero chance of finding it here. We're all talking about the chances, and when I talk about the mean location, well, the mean location is right here in the middle, right? What does it mean, the mean location?
The most probable.
The most probable location, well, not necessarily. No, if I have half my class that are a meter tall and half my class that are 2 meters tall, the mean is 1.5, but no one's there. But it's the exact middle of where I might find it. It means that if I do lots and lots and lots and lots of electrons, all with the exact same system, and I measure the mean of all of them, the average is going to be there. So the average is not the same electron again and again or something like that. It's not that the same electron has many parts to it. No, it has only one location. When we're talking, the statistical nature is about the chance where to find it. Okay, now I have something else. Here I have an electron. Might be here, might be here, and might be here. Okay? What I'm about to explain now is the physical structure of this molecule. I don't expect you to fully understand. I do hope that you'll understand 70% of the following 2 sentences. Okay? The electron can be here, here, or here. Here it's going to have an energy of epsilon. Here it's going to have an energy of 0. This represents the first site, this represents the second site, and this represents the third site. The energy of the first site is 0, 0, and epsilon. However, there is an option of hopping. The option of hopping has an energy delta. If I could start here and move to here, it would require an energy of delta. There's no way of moving from here to here. I do not know where the system is to begin with. If it's here, it's going to stay here forever. If it's here, it can alternate between these two with a certain energy. Okay, there's no reason that you would fully understand what I said now. I do want to show you what are the eigenvectors and eigenvalue. The last 5 minutes were just telling you about the motivation for such concepts, how they're related to quantum mechanics. Let's see what they are.
כאילו קפיצה של רמות אנרגיה, זה הכוונה
No. That's something else. Energy levels of the hydrogen atom, for example, is something that will definitely do not reach the semester. Whatever. Okay, what do? I do the determinanta. I write minus lambda, epsilon minus lambda, 0, 0, delta, delta, 0, 0. And I want this to be 0. This is what? Well, I have minus delta times minus lambda, minus lambda 0, 0, epsilon minus lambda, minus delta times delta 0, 0, epsilon minus lambda. Is that okay?
Yes. You can also take the.
Yeah, you just take this times that. Should I just do this? Yeah, why not? But it's 7.
Okay.
Come on.
So
Joseph is saying rightly that to be more efficient, to just say epsilon minus lambda times minus lambda delta delta, epsilon minus lambda times lambda squared minus delta squared, and I get here 3 eigenvalues. Lambda 1 is equal to epsilon, lambda 2 is equal to delta, and lambda 3 can be minus delta. Now, how do I find the eigenvectors?
you have to substitute.
When's the last time you've done it, Maxim?
ליניאר.
So a year ago.
Yes.
Okay? But it will become in handy, so that's why we're doing it now. So if lambda is equal to epsilon, okay, so I have here if lambda is equal to epsilon, I multiply this by x, y, z, and then I get minus epsilon x
Plus delta y.
plus delta y plus 0, and here I have delta x minus epsilon y, and here at the end I have 0.
That should be equal to 0. Like
Now this should be equal to 0. 0, 0, 0. How can that be? Maybe because x is... Wait a second, am I missing here anything? Or maybe x is... Maybe I should start looking at my notes. Embarrassing. Is it here? Yes. Okay. X is 1. Oh, okay, epsilon x is delta y. So x is delta over epsilon y. On the other hand, I know that this is from equation 1. Equation 2 gives me that delta x is equal to epsilon y, which is exactly the same. No, which will give me that x is equal to epsilon y over delta. How can that be? Only if epsilon is equal to, only if x is equal to y, right? Okay, x is equal to y. I want this vector to be normal. So I'm going to write v1 is equal to 1 over square root of 2, 1, 1, 0. Okay, what is the second one? The second one is if I would take, I need to take now these two. Since I don't have time to actually do it, I'm not very fast about it, I'm just going to tell you what are the 3 eigen.
Goed, is ook niet ergens van mij.
Eigen? Okay, and what I get here at the end is v1, v2 is 1 minus 1, 0 over square root of 2, and v3 is 0, 0, 1. Each one of them, what?
Orthogonal, right?
What?
The 3
Oh, is it?
vectors are orthogonal.
Yeah, actually, I made a mistake here. This is not possible. You should have stopped me. This here is when x and y are both 0.
Yes.
Okay, and z can be whatever I want. It's going to be 1. This leads to this one. Whatever. What I did want to show you here is just again one example of the statistical nature and the annoying and confusing part about quantum mechanics, also the beautiful part about it, is the superposition. This here represents that I'm only at site epsilon. The energy of this one is epsilon. If I'm here, I have an energy epsilon. If I'm here and here, I have the energy of plus and minus delta. So if I have a positive energy of delta, so I'm both at sites 1 and 2. If I have an energy of minus delta, so I'm both at site 1 and site minus 1? What does it mean? What does minus mean? You do see that if I have one energy, I can be in 2 places. How can I be in one place? If I measure the electron and I see it on this atom, I need to be here. I need to subtract these 2. All I'm trying to say here, and I'm not expecting you to fully understand the sentence, so you shouldn't be stressed out about it, is that one location can be a superposition of 2 different energies. And one energy is resulted only sometimes from 2 different locations. It's confusing. This is exactly what we're about to learn in the future of the semester.
Are you talking about the generate?
What?
Are you talking about the generate?
The generate? No, not yet.
No.
We'll talk about it later. Here there's one dimension. There's no degeneracy here. Degeneracy is nivud. We're not talking about degeneracy here.
Two eigenvectors have the same energy.
They do not have the same energy. One has delta. Oh yeah, degeneracy is when two
Yes.
eigenvectors have the same energy. Yes. נבוא את זה כשיש שני מצבים שונים עם אותה אנרגיה. Any questions? Thank you very much. I'll see you next week and I'll upload homework later today.
אפשר להסבר עכשיו בעברית?
The whole thing?
על המצלול. רק על ה... עזוב את המתמטיקה של הדבר.
כן, נראה